So today we're going to talk about project 9 and 10. I've combined them. I only have the project 9 part, which is designing the system and the pump and matching the pump to the system. And then next week, we'll add in the groundwater pump and the reservoir. So what we're doing is we're going to design our system, and then we're going to have a centrifugal pump connected to a reservoir supplying our sprinkler system. And then next week, we'll add in the groundwater to fill the reservoir and also size the reservoir. So then that'll pretty much be it for the semester, because we're not going to have a project 11 because our system is pressurized. So we aren't going to need canals for the system design. Okay. So when you design an irrigation, there's 4 important design constraints. And first, you have to calculate the maximum evapotranspiration. So the system is designed to meet the needs of the crop at the worst time of year, which is the maximum ET time of year. And then the rest of the year, the farmer won't need to use it quite as much, but the design needs to be just for the maximum ET, which kind of makes it much easier to design because you're only designing for one point. Another design constraint is the soil total available water. So the total available water determines the maximum allowable time between irrigations. So, or total available water. So, for instance, if there's 20 or 10 centimeters of water and you have 1 centimeter per day evaporation, then you could irrigate once every 10 days. For a subsurface drip system, this is not important because you pretty much irrigate every day just to keep the soil the same moisture content. But for sprinkler and flood systems, there's an advantage to irrigating fewer times. It improves the efficiency because you have less evaporation from the soil surface, and you might have other sources of inefficiency during each irrigation, such as runoff, and there's other factors depending on the system. So anyway, you take the total available water and you divide by the maximum crop ET, and that gives you the maximum time between irrigations, like 10 days. Another design constraint is soil infiltration rate. So where I used to work, the soils around where I was, it was 0.3 inches an hour. That's how much water you could get in the soil. Well, with sprinkler systems, you don't want to have excess water application because that runs off and that it decreases your uniformity. So you have to check your soil infiltration rate. So we'll do that. Actually, you're going to do that. And then the last constraint is owner preference. And farmers have generally have a preferred irrigation system, maybe even preferred sprinklers, maybe even preferred nozzles, and also might have other preferences regarding the design. So it's very important to talk to them about what they want. Even if there's a better system than what they want, often they don't want that better system. They want what they want. So generally, that's the system they get, is the system they want. Okay. So first, let's look at the maximum evapotranspiration rate for the pecan orchard. And so the maximum ET for certain crops is sometimes available in publications. And we actually went over this last time, but I'm just going to summarize it. So the best way to do it is if you can multiply the crop coefficient by the reference ET for the region. Maybe that's not the best way, but that's the most common way, because you might have some measured ET rates for a certain place, but it really doesn't transfer to other locations unless you use a crop coefficient. So we had a researcher here, researcher and manager of the ASMET website. He's now gone. Paul Brown. He's now not at the university, I should say. And so he did a study of pecans in Sahuarita, Arizona, which is not where we are. We're in Coolidge, Arizona. At least that's where we're trying to put our system. And so the maximum monthly evapotranspiration rate for pecans was 10.8 inches per month. Well, Sahuarita's cooler than Coolidge. And so we can't really use that number directly. We could try to adjust it. But anyway, 10.8 inches per month is 9.1 millimeters per day. So you divide the 10.8 by 30 to get 0.36 inches per day, and then multiply by 25.4 to get 9.1 millimeters per day. But we're not going to be able to use that number because Coolidge isn't as hot, or Coolidge is hotter than Sahuarita. There's also a study from El Paso, Texas, but that's also a higher elevation and a different climate. So their maximum pecan ET was 9.6 millimeters per day. Okay, but in the brown paper, oh, and I just compared, I went to ASMET and actually I went to AI and I said, what's the comparative ET between Coolidge and Sahuarita in June? And it's basically 1.5 millimeters per day higher. So while Sahuarita ET in June is 7.4 to 7.9 millimeters per day, that's reference ET. That's the weather station ET. In Coolidge, it ranges from 8.9 to 9.4 millimeters per day. So quite a bit more. So that's more, that's like 20% more, I think. So if we didn't have any crop coefficient, what we would do is multiply the 9.1 times 20%, 1.2, 20% more, and we'd get a design ET of 10.6 millimeters per day. But we do have crop coefficients. So in that same paper by Brown, and here's the reference for it here, he gives crop coefficients for each week. And so based on the fact that we have monsoon in Arizona, and so it's a little bit cooler, or less ET anyway, during monsoon, June's probably our critical month. And so here's the crop coefficients in June. So around 1, going up to 1.03. And then in July and August, it remains about 1.03. It goes higher here in August, September, October, but that's not really critical because the reference ET is much lower as we get out in that range. So really, we're probably going to have to be concerned about June, possibly July, but monsoon season starts in July. And really, the crop coefficient doesn't increase above 1.03 in July. So probably we should use the June, which is right before the monsoon. Here is the crop coefficient curve. So this was from the same paper by Brown. And you can see that they're showing it's here about 1.03, and then it jumps up pretty high here in October, but we're not so concerned about that. And then here's another crop coefficient curve that he shares from different locations. A couple, I think, are in New Mexico. They have a lot of pecans in New Mexico. And then I think that the green one is the Arizona curve in Sahuarita. Probably reflecting the fact that we have monsoon season here, this little dip down. Not sure why. Not sure about the specific vegetative characteristics of pecan trees. Looks like they go dormant in December. They probably lose all their leaves. Okay, so I did some checks, and what you want to do is you want to find the worst case, but you also want to be aware of risk. So like here's the monthly maximum ET is 10 inches for reference ET in Coolidge. So I've been looking here at Coolidge. So monthly isn't quite as good as like 2 weeks because the irrigation frequency might be closer to 2 weeks. So I'm worried about the worst case for 2 weeks. And you can see that in 2025, we had the worst case. We have 5.4 inches, and this was for 15 days. So I was interested in doing it for 15 days, and maybe I should have done it from June 16th to June 30th. That's probably a mistake. I shouldn't have gone June 15th to June 30th. I think that's 16 days instead of 15. So there's a little bit of an error there. But anyway, what does that tell us? It might tell us that global warming is happening, like they're getting higher and higher. I don't know what it's telling us. But, we do know global warming is happening, climate change. And so we should plan on the temperature getting hotter and drier, which seems to be what we have in Arizona.
And less reliable monsoon.
Less reliable monsoons. Yeah. So anyway, 5.4 inches and probably that's 16 days instead of 15. Here's August. And so it only went up to it was lower, average was 8, and it went up to 9. So here's June, it went up above 10. So we can see that our azimuth ET in June is way worse than August. Is 10% higher. Okay. So what you need to do for your project is you need to figure out the worst case ET for the period with a high crop coefficient. And so I've kind of given away when that is. But also noticing that 2025 is higher than normal. And probably you want to go for a 15-day period of peak, which is probably worse than a 30-day period, because you have fluctuations. And also you have probably higher ET in mid-June than early June. And I think to be safe, considering global warming and the possible need to shut down the system for repairs, I would add 15% to that for your ET. So on top of finding the worst case, I would add 15% for my system design, because you always want to have a safe system design. You want to have what is it called? Safety factor. So that's the safety factor. So for example, if the design ET is 10 inches over a 15-day period, which it isn't, I'm just using it as an example, you'd want to have a design ET of 11.5 inches over the 15-day period. And then in order to find the daily ET, you divide the 15-day total by 15 and multiply by 25.4. So you'll have to go ahead and do that, but it'll be somewhere in the range of 10 to 15 millimeters per day. Any questions? Okay. The next step is to find the sprinkler gross application rate and divide by the evaporation rate to find the net application rate. And so anyway, here is one possible design for the sprinkler system where we have 2 sprinklers per tree and we have laterals going this way. Okay. So remember, the trees are 40 feet apart this way, 30 feet apart this way. So this is a 20-foot by 30-foot spacing. That's the important thing now, because all we're doing is we're calculating the application rate and we're just going to use an equation based on spacing. So here's just a look at it without the trees. So here I have a possible submain, and then I have sprinklers. So the lateral's going along, and then I'm slotting over, digging little trenches right between the trees. My sprinkler lateral can't go down the tree row exactly. It has to be a little bit away. And then I can slot over to put the sprinkler right between the trees, because the sprinkler lateral will be covered over by dirt. It'll be like 18 inches deep, or maybe 12 inches deep in Arizona. We used to have them 18 inches deep in Washington, partly due to the freeze. I don't know there's usually a rule in each state as to how deep they need to be, or a rule of thumb, let's say. Although maybe if you're getting funding from the Natural Resource Conservation Service, They might have a specified depth that you have to put your pipe.
Is that the main reason for burying this trees? That would make sense.
Well, in Washington, you can always just blow the pipes out before the freeze because you never irrigate in winter. So you can just do that. But basically, you're protecting it from tractor wheels and so on, from cultivation instruments, cultivation. So maybe 18 inches is also for cultivation purposes, protect it from the wheels. Might be other reasons to bury it a certain depth. Usually in every area, they have ways they do it. And that's the way you should do it. In my opinion, after working as an irrigation designer / engineer, my rule of thumb is never be the first person to try something new, because you don't know why it's not being done right now. Even if they design a new drip emitter or a new sprinkler, I'm not going to be the first one to try it because I don't know what's going to go wrong. Something's going to go wrong. I can almost guarantee you that something is going to go wrong with a new thing. That's one reason farmers don't like to change. They don't like new things because they've learned from experience that new things often don't work. And they don't want to be the research farm for the new thing. For example, in Washington, there was one apple orchard where they put in this new rotor sprinkler. You know, rotors are very popular now, rotor sprinklers. Well, all of them froze and broke. So they had to replace 10,000 sprinklers. Things like that. You know, one time a guy recommended a filter to me, and he said it would work on this canal water. And we were up at midnight putting the sand filters back in so the farmer wouldn't lose his peach trees. It's things like experiences like that that make me say I'm never going to be the first person to try something new. Or if I am, I'm going to do it on a very small scale, try it out at a small scale, or ask somebody to do some research on it. I'm never going to do an experiment in a farmer's field. Because farmers can get very angry. One of the farmers with those filters was mentioning guns, you know, and he was very well known for being a very angry person.
Nice.
Okay, so for instance, here I'm recommending using a Hunter LA wobbler for the pecan orchard. If nobody else is using a Hunter LA wobbler for a pecan orchard in Arizona, I'm not going to put one in. You know, I'm going to do whatever somebody else is doing. I'm only recommending the Hunter LA. I think I've seen them out in the farms under trees. So I think they are being used. The reason I'm recommending it is we have such evaporation problems in Arizona with sprinklers. This has large drops. So, but I wouldn't actually put one in without seeing it in other people's farms and seeing that it works. For example, maybe insects get in it. Maybe bees lay eggs in it. There's just so many things you just can't plan on. Maybe the water is corrosive towards this sprinkler. Probably not because it's plastic. There's just maybe there's sand in the water that degrades it. There's so many things could go wrong with a technology that anyway, you have to be very, very cautious about using a new technology. The best way that farmers have to validate a new technology is they try it on a very small part of their farm, and then they expand and get bigger. You know, you don't want to commit a whole farm to some new device. Anyway, let's assume that the Hunter LA wobbler is okay. And actually, you guys, for your project, you don't have to use a Hunter LA wobbler. You could use some other sprinkler. You might prefer a sprinkler that reaches across the whole distance between trees, like 35 feet of radius. This only has a 20-foot radius. Okay. Anyway, we're going to make the calculations here in this example with the Hunter LA wobbler, 8.5 liters per minute, 14.2 meters cubed per hour. And here's how you calculate the precipitation rate in metric units, millimeters per hour. You take 1,000 times the meters cubed per hour over the meters by meter spacing. So here's the meters cubed per hour. Here's the meters by meter spacing. So you'll go ahead and make that calculation. And then for the application rate, remember we have evaporation. So I think I would multiply it by 0.9 to get the net application rate. And then you can compare that to your infiltration rate of the soil, which you'll find in Web Soil Survey for the Mohall Sandy Loam. Remember, we're putting this field on Mohall Sandy Loam soil. Okay, so that's one thing. Check to make sure the application rate doesn't exceed the infiltration rate of the soil. And then next, we're going to make our irrigation schedule. So we're going to calculate the required depth of application, system runtime, frequency of irrigation, and that's going to be based on the available water capacity, the root depth, and the max ET in summer. So first, you'll have to look up what's the depth of pecan roots, and then you'll use your AWC calculations for the Mohall Sandy Loam soil to find the total available water in the soil root zone. You might want to multiply that times 62% if you think there's going to be a 40, 30, 20, 10 extraction pattern in the soil, where only the upper roots take most of the water out. The lower levels of the soil might not be that useful for getting water to the trees. I don't know. You can look that up, or you could not. I don't care. And just telling you that that's something you sometimes do. And also for my sprinkler design, I only have 20-foot radius sprinklers, so that they're not going to uniformly apply water to the field. So I think I would reduce my TAW by about 1/3 for estimating the maximum time between irrigations. Okay. Okay, then you'll use your adjusted TAW and divide by the ET rate. So let's say your TAW is 100, your ET rate is 10 millimeters per day. You'll take 100 divided by 10, and that'll give you 10 days between irrigations. Next, you'll find your application time per irrigation by dividing the TAW by the unadjusted application rate. So I think the line between sprinklers is going to have about the application rate of that you'll calculate with this average equation. It won't be as much in the middle between trees, but I think right in the line between the sprinklers, it will be as much. So then let's say your TAW in that direction, or your unadjusted TAW is 120 millimeters, and you're putting on 8 millimeters an hour, then you would leave your irrigation system on for 15 hours. Well, one thing to realize is farmers don't like irrigation schedules of 15 hours. They like 12 hours, 24 hours. So what we used to do is we used to like pick a new nozzle and so on, so we could get 12-hour and 24-hour irrigation schedule or run times. Because they don't want to go out like 2 o'clock in the morning one night, then 3 o'clock in the morning the next night. Now with automatic controllers, it's not such a big deal, you know, or it's a giant farm and they hire irrigators, you know. So it might not be a big deal, but it's just something to remember that if you have a other than 12 or 24-hour irrigation schedule, you might have an angry farmer. You can see that I mention angry farmers a lot. Okay. Actually, farmers are generally quite nice people. It's just, you know, if their whole livelihood is wrapped around their crop, they're not going to be very happy if you screw up their crop. Okay. Determine the number of zones required on the farm based on the irrigation runtime and frequency of irrigation. So the number of zones depends on the application time per irrigation and the frequency. So let's say there's a maximum of 10 days between irrigations, and each zone requires 8 hours of application per irrigation cycle. And remember, we're only applying water for 8 hours per day on this pecan field. So that means you would have 10 zones. If you're running 8 hours per day or per cycle, and you have 10 days between cycles, you'd have 10 zones on your farm. So then you have that 400 by 400 meter area, and you would divide that into 10. And you'd water each of those 10 zones one day. Okay, so once you divide your farm into zones, and this might be the zone. And what I'm showing here, I think, is I think this is about, I think I have about 6 meters between sprinklers. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 sprinklers on one side of the submain. This is the submain supplying the laterals. So 11, I have 22 sprinklers, 6 meters apart. So 22 times 6 would be 100, 130. So I have 130 meters if I had this design. And remember, our field is 400 meters wide. So I would have 3 of these zones with submains going north-south. And then I'd have 3 of these zones going this way, okay? Then you have to figure out, how do I divide it by 10? So then you would have, one way to do it would be to have the total number of sprinklers on the property divide by 10, and then you'd want that number of sprinklers in each zone. That would be the best way to start. Or you could just kind of eyeball it and say, well, I've got 3 this way, so I probably need 3 this way, so that makes 9. So maybe you'd have 9 zones, you know. That's where the little bit more art than science comes in. You're just kind of looking at things and trying to, there's no like real right answer. You're just trying to make it work. Okay, so you'll find your number of zones based on your frequencies, and you divide the field into zones, and then you'll figure out your valve locations. So let's say this is a zone. Okay, this is a submain. So you'd have a valve at the beginning of the submain, and then it would supply directly all these laterals. So that would be one of your 10 zones. Here's your valve, and then your main line would be going along at the beginning of the submain. Okay. Or maybe you'd have to bring your submain back to here where the main line is. That's another thing where it's like just making it work. So you have a main line. So the definition of a main line is it's before the valves. It's not connected to any laterals. The main line supplies the submains. Then you determine the total flow rate and pressure requirement per zone. And I think I should have put these two together. Find the system curve, because that's part of this. So just as an initial cut, you could say, okay, I have 100 sprinklers in each zone, and each sprinkler uses 2 gallons per minute. So I need 200 gallons per minute to the zone. But what you can do is, oh, and also you have a minimum operating pressure. Remember, I think for the example in the project, it was 10 meters pressure. For the midterm, which is this one, I think it was more like 30 meters pressure or something. I can't remember exact. 28 meters pressure. Okay. So anyway, what you do, you design your lateral here, so this is where you'll specify like how big each of these pipes are, like 1 inch, 1 inch, 1 1/4, 1 1/4, and up to 2 or 2.5. And then starting this way also, 1 inch, 1 inch, 1 1/4, up to 2. Okay. And that would be your lateral. And remember, this direction, I have no slope. I have no slope in this direction. So the lateral going east, the lateral going west has the same design. So I would have zero slope here, zero slope. And I'd specify the number of sprinklers, 10 or whatever it is. And I have my distance between sprinklers, 6 meters actually for the 20-foot sprinklers. And then I would figure out my diameters using these drop down menus. And I would have a design for my laterals. Then what you do is you say calculate lateral coefficients, and it's going to give you a lateral equation. So the lateral equation for this one, not this particular one, I probably did it before, is 26.7 times x to the 0.47. X is the pressure. So that's the lateral equation. Then you go to the submain page in the same workbook, and you put in your lateral equation here. So here's my lateral coefficient, 7.9, and my lateral exponent, 0.531. Okay. Then you design your submain. And the submain, that's these pipe sizes. Okay, so it's 40 feet between laterals. No, 30 feet. So that would be 9 meters. And then I would design, and I have like a 0.02% slope here. It might not be important, but remember, you have pressure loss along the laterals, but you also have pressure loss on the submain. So this sprinkler is going to be quite a bit different than this sprinkler if you have too much pressure loss in the submain. So you have to specify pipe sizes such that you don't have too much pressure loss in this submain. And I think I would definitely try to go downhill here, although the downhill is almost nothing, 0.02%. So I guess I wouldn't worry about it too much. But anyway, that 20% pressure variation applies to the beginning of the submain and the end of the last lateral. You can't have 20% just on the lateral. You also have to consider the submain. So you have your lateral equations here, and then it'll calculate your friction loss between laterals. And so I've gone from 44 up to 47, which isn't great, but then I can calculate my submain coefficient. And so that is 97 times x to the 0.5 or something. So that's the system curve for the whole system. That's the so there's always this term called, not always, there's this term called system curve, which is how does your system respond to pressure? Like if you give it more pressure, your sprinklers are going to flow more. And so there's this relationship. Okay. So here's a system curve, this blue line, the system curve. We give it more pressure, it has higher flow rate because we're connected to sprinklers. Okay. Then what you need to do is we have this 400 by 400 meter field. I'm not going to require you to say it's like 350 by 500. Just you can if you want. But let's say we just have this 400 by 400 meter field. And I showed you where the location of the orchard is. I want you to add a reservoir to the property, considering maybe where the pump is and the groundwater pump, and maybe an open, there's that open space on the west end of the property. But anyway, you need to add a reservoir to the property. And then you need to put a main line from the reservoir to the field. So you'll have like a 4 meter pressure loss or 1 meter pressure loss in the main line. You have to add that to your system curve. And also, you might have a 2-meter pressure loss in your valve and a 3-meter pressure loss, and maybe you have a filter, some kind of filter. Maybe you have a sand filter or a sand separator. But if you think you're going to have a filter, you need to add maybe 3 meters of pressure loss in your filter. So if you have the main line, the valve, and the filter, then you'll add 9 meters to your system curve equation. Then you need to find a pump online that has the appropriate flow rate and pressure for the zones. And so these are available online now. They used to be just in catalogs. You know, we used to have a catalog on our desk and flip through it and look at pump curves. But here are the pump curves for the Berkeley B4JBP BH pump. And so they have head on the left. This is what you'll be working on this week in chapter 9. And gallons per minute on the horizontal axis. And this is a fun part of irrigation design. What you do is, let's say you know you have this operating pressure and flow requirement. You pick an impeller and a horsepower. Okay. And so each pump, they can trim the impeller. The impeller is the thing inside the volute, which is the thing. The impeller is what goes around and gives pressure to the water. They can make impellers larger diameter or smaller diameter, but depending on what you need. And so this is the impeller curve. Okay. If you're operating here, you cannot use a 30 horsepower motor. The motor horsepower cannot go below the operating point because otherwise you'll burn up your engine, your motor. So like if my operating point was here, I would have to buy a 40 horsepower motor. So they can attach any horsepower motor to this pump. And so I would find my operating point. Then I would I'd say I want a 12 3/8 inch impeller and I need a 40 horsepower pump. Now, if for some reason they operate that pump without pressure against it and it goes out here, then the impeller curve is going to be above the horsepower curve. That's going to burn up the motor. So it's very important not to just run a pump without any pressure against it if it's designed to run with pressure against it. So that's anyway. You cannot have an impeller point above a horsepower curve. So here's the horsepower curves here. They're not curves, they're lines. And then here's our impeller. So you pick a 12 3/8. You can pick an impeller between the 12 3/8 and 11 3/8 here. But that's going to cost you money because it takes a special trim. So these are the standard trims. And you could say, well, I need an 11 5/8 because my operating point is right here. You could say that. And they would do it for you, but they would just charge you an extra $100 or $200. Then the other thing you need to look at is your efficiency lines. So notice this operating point is between 80% efficiency and 75% efficiency. So the pumps work best at these operating points that are near the maximum efficiency. So the maximum this pump will produce is 80% efficiency. So, and one thing I wasn't clear on is, let's say my flow requirement was 960. So that's why I picked this red line. And my pressure requirement is 130. And notice this is head and feet and gallons per minute. So that's why I'm drawing these red lines. And then I would pick my impeller, then I would pick my horsepower. And then I would see, is this at an efficient operating point? Yes, 77 when the max is 80 isn't bad. So I would probably say, yeah, that's pretty good. But I would look through the catalog in the old days or through the web these days, and I would find the best pump. I'm sure right now they have like tools to find the best pump. You just give it a operating pressure and a flow rate, and it'll pick it for you. But there's catalogs online that you can look through, and it's possible even one of the these are called pump curves, even one of the pump curves in the chapter will do the job for you. So you're welcome to pick that if it's good. Okay. Then you need to make an equation for the impeller that you chose. So like you have a series of pressures and flow rates along this curve. What you can do is there's a system and pump curve worksheet in your chapter 9 workbook called System and Pump Curves that allows you to put in flows and pressures, and it'll calculate an equation for you. And then it'll find the operating point. So here's the equation for the pump curve. Here's the pump curve. Here's the equation for it. Here's the system curve. And then this red here will find the operating point in the spreadsheet. So that's where your pump and your system is going to operate. And that's it. And then next week, we'll add in the reservoir and the groundwater pump. All right. Is there any questions?